We are here today to talk about why Star Schema is your best choice in Power BI. That's a kind of session that I would have never thought it would be useful because, Star Schema is the best friend of any business intelligence model. Nonetheless, the question always appears. People always ask whether a star schema is better than a single flat table or a Snowflake schema or any other data model. So the goal of the session is to understand it better. We're going to look at different models. Well, actually the same model, but modeled in three different ways. First, we introduce what a star schema is and what are the differences between a Snowflake, a star schema, and a flat file. And then we look at performance. So we look at the easiness of writing DAX code. We look at the differences between the models. And I'm not going to spoil anything, but the star schema is the best choice. What I want to show you is the reasons why it is the best choice. So that if you have to discuss with your boss or with your customers about different models, you have tools in order to explain them why using a single flat file is the worst choice and why a Snowflake is just a suboptimal choice, and it has several issues. But before starting, who I am. I'm Alberto Ferrari. I work with Marco Russo at SQLBI.com. We publish articles, we do trainings, we do online trainings and live trainings. We teach everything about analysis services, tabular, Power BI, and specifically, I think we are experts in the DAX language. The Definite Guide to DAX is the book that tells everything that we know about DAX, and then we also do consultings, and we are BI experts working mainly with the DAX engine. But I'm not here to sell myself. The goal of today is to start talking about different types of data models, and then what kind of test you need to do on your model in order to understand whether your model is right or wrong. There are different ways of modeling your model, modeling a data model. The single flat table, what I call the believers in the Excel way. In Excel, you model everything with a single flat table. And with the advent of self-service BI, a lot of users move from business or Excel, and they start creating models in Power BI. They were used to work with a single table, and so they continue doing that. They create everything into a single flat table, believing that that is the right way to work. There are, indeed, some advantages in using a single flat table. Well, the model is very simple because everything is just in one table. But there are also a lot of disadvantages that we are going to look later. Then the star schema. If you go for a star schema, that means you follow the Kimball methodology, you split everything into facts and dimensions. That is by far the best way of modeling your data model. For a lot of good reasons, we have started working with star schemas many years ago. Therefore, all the articles, all the DAX code that you will find, all the engines are built on top of star schema. They think that you are going to create a star schema, and everything is optimized to work on a star schema. If you use a star schema, let me tell you, the thing is, you don't have to worry about a lot of details that you have to worry about if you use a different model. So going for a different structure is only creating issues. And then the Snowflake. Snowflake is a different way of modeling where you have relationships between dimensions. It's not that bad. It doesn't have really advantages. It has several disadvantages, but those disadvantages are not as bad as the single flat table. So it's not wrong to use a Snowflake model, even though it's not optimal. You're not working in the best possible way. So you are creating yourself issues for no particular reason, because it's neither faster, nor better, nor has any other advantage. It has only some small disadvantages. Let's look at the models into detail. What I did in order to prepare the session was to take the Contoso model, a version of Contoso model that is not very large. It contains only 10 million rows in the fact table. And I denormalize everything into a single flat table. The first model, the flat table, has only one table, sales, that contains everything. You see, it has the address of customer, the age, the birthday, the brand of a product, the category of a product, the color, the continent of the customer, and then the customer key and other columns. everything is denormalized into a single table. That means attributes of product, customer, data are all stored into a single table. Of course, the original data source was not built that way. I had to write M code in order to denormalize, to denormalize everything into a single table. The original model was actually a star schema. If you build a star schema, that means you follow Kimball methodology. You have your fact table, sales, and sales contains the customer key that points to the customer, and all the attributes of customer are stored in the customer table. The same for date, for product, and for store. All the columns that are here in product, date, customer, and store are in separate tables in a star schema, and they would be completely denormalized in the sales table if you go for the single flat table. One of the rules of star schemas is that you can have one-to-many relationship where one is date and many is sales between the fact table and the dimensions. And that's the only type of relationship that is allowed in a star schema. You cannot create relationships between different dimensions. You cannot reverse these relationships, and you will never use bidirectional relationships anywhere, because bidirectional relationships are bad. But we will see that tomorrow in a different session. So you are only allowed to have one level of indirection between sales and data, and you cannot have other tables here around. You cannot create relationships between different dimensions. These are the rules of Kimball. And they have a meaning. They make the model easy, they remove ambiguity, and they make the model very easy to understand. If you show this model to anybody, any user, they will quickly understand it, that we have customers, date, product, and store. Therefore, in a store, a product was sold in a given date to a given customer, and relevant information are in sales. So the best advantage of star schema from a user perspective is that they are simple to understand. Sometimes people create slightly different models. Again, this is a model that I created just for the demo, but you see that this is no longer a star schema because we still have sales at the center. We have date, customer, store, and product, so the tables that build a star schema. But then we have other tables. We normalize the attributes of a country into another table, country. And we created a relationship between country, customer, and finally sales. This shape of the data model is what is called a snowflake. In a snowflake, you basically have chains of relationships that start from the center table, the sales table. They reach a first level of dimension, but then the relationship continues. So from sales, you go to product, then to subcategory, and finally to category. Snowflakes are in the middle between an OLTP system where everything is deeply normalized and a star schema where everything is denormalized only for the main dimensions. What are the advantages and disadvantages from the point of view of the performance? That is what matters most from the point of view of this session. Well, if you think about the flat table, any query that hits the flat table will not use any relationship at all. You have a single table to scan. And we know relationships are expensive. Whenever you need to traverse a relationship in any database, you need to pay a price for that. And the single flat table does not have any sort of relationship. If you want to compute the sum of sales and group it by category or by city or by country, you can do that easily by scanning a single table. So we have the idea that a query that runs on the flat table is going to be fast because it only scans one table. Whereas if we go for the star schema, we have to pay one level of indirection for every relationship. Therefore, the query will be slower and slower as more dimension we add to the model, because every time the engine needs to traverse a relationship, that needs to happen at query time, and we have a price to pay. From the relationship point of view, the Snowflake looks like it's going to be worse, because we have a longer relationship that start from, what is that? Country to reach sales, or from category to reach sales, I need to traverse multiple relationships. Therefore, we would expect the Snowflake to be the slowest one overall. And the main topic that the followers of the flat file, the flat table, point out is that not having any sort of relationship makes the model way faster. So what's the point in building a star schema? Specifically, if maybe I already start from a flat file, so what I receive from the outside is already a flat file, why wasting time normalizing it into a star schema where I can just load it and be happy? The thing is, things are not that simple. As we are going to see now with the demos, there are advantages and disadvantages. If you go for the single flat file, the model is larger, much larger than you would have with a normal star schema. It's slower to query. Even though I told you no more than a couple of minutes ago that it is expected to be faster, it is actually faster if you run very simple queries and if you do not write complex queries. But in a regular report where you have multiple queries that need to run on top of your flat file, the query end up being actually slower. And the DAX code tend to be much more complex because not having the structures of dimensions that you would have in a regular star schema, you need to write DAX code that is harder, and most importantly, it is error prone. As soon as you change anything in the model or you change the report, your DAX code will no longer work as expected. Star schema, well, as you might have guessed, I'm a big fan of star schema, so to me it's a perfect model. The only drawback of a star schema is that you need to build it. You need to decide what are the dimensions, you need to decide what the fact table is, you need to write ETL code in order to build a star schema, because it's very unlikely that your original data source is already a star schema. The Snowflake, well, the Snowflake, as I said, is not that bad. It's very close performance-wise to a star schema, because the additional levels of relationship that you are adding with the dimensions that are far away from the fact table is not expensive. A query will run at nearly the same speed as a star schema. Nonetheless, by creating snowflakes, you are increasing the number of tables. And users, they do not like to have a lot of tables in their report. They want to have a small number of tables with attributes that are easy to understand. If you increase the number of tables, just this simple fact is going to make the report and the experience from the user point of view worse. There are actually no specific reason not to denormalize a snowflake into a star schema. There are some. I'm not saying that snowflakes are always wrong, but there are really very few reasons. And worst of all, as soon as you have a snowflake, you need to learn about one of the most complex topics in DAX, which are expanded tables. Expanded tables is a complex and advanced DAX topic that most DAX developers never think about. And the reason is quite clear. You do not have to think about expanded tables as long as you have a star schema and you write DAX code the proper way. But it's hard to see a problem with your DAX code because of expanded table if you are working with a star schema. Whereas as soon as you have a snowflake, there expanded tables become a problem. And you can write DAX code that looks perfectly correct, and it breaks, and it does not produce the correct number, and it will drive you nuts just because you do not understand properly how the table expansion goes inside the model. With all that said, I don't want to keep this introduction so long. The entire session is all about demos. So we are now going to open the report. We analyze the performance using a simple dashboard that has a category, subcategory, and then slices by year and color the sales amount. So it's a very simple dashboard, but it is already useful to start investigating about the different performances. So let's move to the demo. And here I have the three models. I have the Contoso 10 million fat. This is the model containing 10 million rows in the fact table. And as you see, the data model contains only one table, sales. Everything is denormalized here. Harder than expected. We have all the columns in a single table. And we have the report that is slicing by category and subcategory the years. 17 million is the value. Then we have the star schema. Star schema is slightly better. We do have sales and then dimensions around it. Customer and date. And with that said, the report shows the very same numbers slicing the same value. It's the very same content, just shaped in a different way. And finally, we have loaded here the third model, that is the Snowflake schema. In a Snowflake, we have sales, and then we have a chain that starts with country, goes to customer, and then to sales, and another chain that starts from category, subcategory, product, and finally sales. Of course, if I place a filter on category, I need to traverse the entire chain of relationship to reach my point, to reach the sales table. Nonetheless, the numbers are really the same. And the first thing that we want to understand is whether the claim that not having to traverse any relationship, it makes the model faster or not. How can we do that? That's quite easy. We have a report, and we can just check how long it takes to render this report with the three models in order to get a better idea of the differences. But actually, before that, I started the introduction saying that denormalize everything, the model becomes larger. So the single flat table is going to be larger than the star schema and of the Snowflake schema. And it's interesting to understand how much larger. We can take a look at that with DAX Studio. So let's go for the star schema. Let's start DAX Studio. DAX Studio is the tool that we are going to use to analyze performance, size, and everything else. If we look at the matrix of this data model, this is the star schema. We can start from the summary. 10 million rows means that the star schema uses 2.61 gigabytes of RAM. And the 261 gigabytes of RAM are split into different tables. We have the sales table that uses actually 2.6 gigabytes of RAM, and everything else is just tiny. That is what you would expect from any star schema. You always have very small dimensions and a very large fact table. Therefore, it's absolutely normal that the size of the model is entirely in the fact table. But the thing is, what is important is that we have 2.6 gigabytes as the size. Now, let's create a new query, and this time we connect this to the flat file. It shows an error, but actually it should be working, hopefully. Let's look at view matrix. It does. This is the same content, same numbers, but it's in the flat file. You see, it's 10 gigabytes, which means 4 times larger. It's way larger than the star schema. And if we look at the tables, everything is in the single table that contains 10 gigabytes. So we go from a sales table that uses 2.6 gigabytes to a sales table that uses 10 gigabytes. Why is that? Well, the thing is, the size of a column in tabular depends on basically two details. The number of rows, that despite having said first is the least important one, and the cardinality of the column. The larger the cardinality of a column, the larger the column will be. But both aspects are important. Look at the star. Let's look at the star schema. If you look at the star schema, the size of the customer key column is much larger. Here it is, the size. The size of the customer key is much larger, for example, than the size of the product key or the size of the, here it is, of the store key, which only contains 74 values. So the number of values is smaller, and the size is different, 49 megabytes against 600 megabytes for the customer key. The same number of rows, the only difference between the two is the cardinality of the column. But still, both aspects are important. And the only column we have about customer in the sales table is the customer key. As you see, there are no other information about the customer. So we have a column with a large cardinality, but it's only one column. Then all the attributes are stored in other tables. The customer table contains, for example, the zip code, which is 18 megabytes, the birth date, that is 5 megabytes, the age, that is 1.4 megabytes. There are small columns because They have a small cardinality and, most relevantly, are stored in a small table. The customer table contains, let me see, 2 million rows, so it's quite small. Let's look at the same column in the sales table, in the single model. Customer key is already larger. You see that the column size of the customer key is larger. Why that? Well, basically, having more columns in the table, the algorithm that sorted and tried to find the best way to compress the data had better chances of finding the optimal sorting with a smaller number of columns, as it did in the star schema, than it did with the flat table, because with a single table, there are so many columns that finding the optimal sorting is kind of hard. But look, for example, at the name, the address, or the birthday. The birthday uses 455 megabytes on the single table model, whereas the birthday uses only 5 megabytes on the star schema. The number of values is the same, but here the number of rows is quite important because we increased by a lot the number of rows, and we have to repeat the same value for all the instances of the customer. So by denormalizing everything, we are increasing by a lot the size of the data model, which might be not a problem. So if you do not have problems with RAM, if you have a lot of money to spend with Power BI licensing and you are able to use as much RAM as you want, you might think that, well, increasing the size is not actually a big deal. Before we leave the topic about size, let's do the same with the Snowflake schema. So we connect with the Snowflake, and then we look at the matrix here. And if we look at the summary, you see that it is really slightly larger than the star schema. So the difference between the star schema and the Snowflake schema is quite irrelevant. We do not even think this as being a difference, because on the other hand, we have a difference between 2.6 and 10 gigabytes. So it is an important difference. But we might think that that is not that bad. We are willing to pay the price of a star scheme, the price of space, if we have an increase in performance. So now let me open the flat file. Here it is. And we analyze performance. Here I'm slicing by year, color, and I'm placing a filter on category and subcategory. This is probably going to be the slowest query, so we need to monitor it. And to do that, that's quite easy. We just launch the performance analyzer, we start recording, refresh the visuals, and here we have our numbers. We have 2 slicers and then a matrix that, as you see, doesn't seem to take a lot of time to be executed. But we want to have a better picture. So let me copy the query. Let's go on the DAX Studio. We are here. Let me place the flat file first, and we place the query. As it always happens with queries executed by Power BI, they look quite long and complex, but actually that's just because they are auto-generated. The core of the query is here, the summarize column that groups by year, color, places the 2 filters with the 2 slicers, and computes the sales amount. Everything else later is basically useless because it's only useful to build the visual and have it shaped in a specific way. So we can just kill everything and evaluate this part so that the query is actually much simpler to execute. And let's see how long it takes to execute this query on the star schema, on the flat file. To do that, we need to enable server timings. We have the server timings here, and we run the query. I'm not interested in the result. I'm interested only in the server timings, for which I do not have anything. Let's try that again. No way, so let's try to disable and enable again. Okay, so let's try to open a new instance of DAX Studio. We connect with the flat file, enable server timings, run it, and finally we have it. There is a single query being executed, as we would expect, and this query, let's go for a bottom layout that makes it easier to read the code. You see that it groups by sales year, sales color, computes the sum of the expression that computes the sales amount from sales. There are no joins and nothing else. There is just a simple query that takes 2.5 seconds. I'm not interested in the total execution time. I'm interested in the storage engine CPU, because that is where the difference between the two is going to be relevant. 2.5 seconds is the time required to execute the query on the star schema. Let's do the same on the flat file. Let's do the same with the star schema. I need to connect this time to the star schema. Click on connect. Hope that server timings is going to work this time. If I run the query as it is now, it's not going to work because I'm referencing column in the wrong table. Category will no longer be inside the sales table. So we just copy this, and then sales year need to be in data, and color is going to be in product. And sales amount is just in sales. So now I have server timings enabled. The query should be able to execute. And this is going to take longer than the previous one. You see, it takes 5 seconds. So the claim that the flat file is actually faster looks to be true. 2.5 seconds against 5 seconds only to execute this query. And the reason is relationships. Whenever you want to traverse a relationship, you have to pay a price, and that price is quite relevant. We can do the same also with the Snowflake schema, but we will probably not see anything really exciting. That is going to be around the same speed as the star schema. So we enable server timings. Now the category is in its own table, category. Subcategory is in the subcategory table. Product color and date year, they should be correctly the same. So if I run it and look at the server timings, that I expect it to be around the same time that it took on the star schema. So Snowflake and star schema, they are likely to be very close one to the other. And you might wrongly assume at this point that, well, the flat file is actually a good option. But you need to pay attention that the query that fills the matrix is not the only query that is actually executed. There are other queries. If we look here, we have two slicers. One is a slicer on category, and the other one is a slicer on subcategory. Now, when the engine needs to produce the content of those two slicers, what it needs to do is gather the values of the columns that you place in the slicer. And here is the biggest difference between the flat file and the star schema. When the query needs to be executed on the flat file, to gather the values of the category, you need to scan a table that is the fact table containing 10 million rows. So it's a very large table that needs to be scanned only to grab the values of the columns. And you cannot just grab them by looking at the dictionary in Vertipack. That would be beautiful. Because actually, the slicers, they filter one each other. So the filter on subcategory, the values of the subcategory depend on the category, and the value on the category depend on the subcategory. That is why you need to run a query over the entire table to grab the values. The same query can be executed on the star schema, but in the star schema, the only table that you need to scan to grab those values is the product table. You never need to go to the fact table in order to retrieve the relationship between category and subcategory that is stored in the dimension. So I would expect the query that fills the slicer to be much slower in the single table model than it is in the other model. And we can check that. We can just grab the query from the slicer, go in DAX Studio, and execute it. You see that the query is basically calculate table values of sales category with a filter on subcategory. As we did earlier, we can get rid of everything and just evaluate this part. Now this is the flat table, so we run it and it doesn't work. We run it again. Look at the server timings, and again, it took only 47 milliseconds, but it is half a second of execution time. Now, it's half a second of execution time to grab a result that only contains a string, cell phones. That is the price that you need to pay whenever you execute a query against the fact table. Every time you want to grab a value from any column in your model, you need to pay that half a second of CPU time. If we do the same query in the star schema, then we have this time product. And the same here. You can already see from the shape of the query that the only table that I'm querying is the product table. So if I run this query now, the storage engine CPU right now shows 0. If we run a few times, at some point we will see a number, but it's never above 8, 10 milliseconds. The difference in gathering simple values between the two models is huge, whereas the difference in running complex queries is not that large. Look at that from the percentage point of view, because here we have 438 milliseconds. That is around 100, 200 times slower than querying the star schema. Whereas for the complex query, it was only half time. So it was twice the execution time. And besides, the number of slices and the number of graphical entities you have in your model is likely to be very, very large. That is why assuming that a star schema, a flat file is better is actually wrong. You are not getting the best out of from the performance point of view. You have a slower model that is 4 times larger. Not a big deal. Moreover, if you start writing DAX code, things are not that simple. Let's pretend that we want to compute a calculation like this one. I'm slicing by brand and computing the sales amount, and I want the percentage of the given brand against all the other values. If I write that in the star schema, in the flat file, that is a simple calculation. Let me see where my code is. It's called percentage. How do I compute that? Well, I compute the sales amount, and I divide it by the sales amount where I remove any filter from the sales brand. I need to remove the filter from the brand column in the sales table, because that is where I have my information. And the numbers are right. I'm not claiming that they are wrong. You can easily compute the value this way. The problem is, as soon as you change this report, it's going to stop working. Why that? Well, let's pretend that instead of slicing by brand, I want to slice by color. I just get rid of the brand, I choose the color, place it in my report, and suddenly the report shows 100% everywhere. Why that? Well, the reason is my percentage is removing the filter only from the sales brand. Not removing the filter from the color, this percentage is going to be wrong. Not something that cannot be fixed. You can go here and add that you also want to do that by sales color. And suddenly the report will start working. But you know users, they tend to use our tools believing that they should work. And so that at some point they get rid of the color and they add the continent. And again, my calculation is going to break. Or they add another attribute from the product table. Let's pretend that instead of the color, they use the category. Again, same problem, 100%. If you were to write the same code in the star schema, things would be very, very different. Because in a star schema, I need to build the report. So let me build it. I forgot to create that. So we can simply copy this. Go in the star schema. Paste it, it's not going to work. Okay, copy, paste. And then we get rid of this, and we need to place the category from the product. And we also need the percentage. We have the code here, percentage against the product. We create a new measure. What should I use here? Well, I can use, I need to use actually product brand and product color. And at this point, this is going to work the very same way. You see that it does not work with the category. Let me do that again. I want a percentage. It doesn't work with the category, but it works if I slice it by brand. If I slice it by brand, let me try. Oh, that place it on the column. I still have to understand why sometimes it places it on the columns instead of on the rows. So it works by brand, it doesn't work by category. But the big advantage of using a star schema is that you have a place where you can remove the filter from all the columns of the product at the same time. It's enough to get rid of the column names here. You just remove the filter from the product, and suddenly that removes the filter from any column in the product table. Writing the code this way results in being more reliable, easier, better, faster to author, faster to debug. You only have advantages by structuring your model so that you have a place where all the attributes of the same entity are grouped together. From the DAX point of view, you have the option of removing filters or placing filters on a single table. Now, there's not time to go into all the details, but that would be true also for placing filters. Whenever you want to filter any column of the product table, that filter would need to work only on the product table, a small table, instead of filtering the sales table. So as soon as your code starts to be more complex, the advantages that seem to be relevant on the single table are slightly disappearing, whereas the size of the model still is there. The model is still larger for no particular reason. So you have a larger model that is actually slower and where the DAX code is worse to author. And what about the Snowflake? Well, the Snowflake does not have the problem of from the DAX point of view. So from the DAX point of view, the Snowflake is not that bad because the Snowflake has only more tables, but you have actually more places where you can remove all the attributes of the country or all the attributes of the category or the subcategory. So again, you might conclude that it is not that a bad idea to start creating snowflakes because you are modeling the model better. So you have more tables and more places where you can write your DAX code. But actually, the thing about snowflakes is that as soon as you create a snowflakes, you need to worry about expanded tables. The code we created before was the percentage of the sales amount against all the products. What if we want to compute something different? I want to create a report like this one. Not this one, but the one on the star schema. Where is it? OK, I want to build a report like this. I'm slicing by category. I have all the subcategories on the rows, the sales amount, and this percentage is the percentage of the given subcategory against the category. So I want to remove a filter from the subcategory. Keep in mind, when you are computing this value, you have a filter on the subcategory, a filter on the category. If I remove the filter on the subcategory, what remains is the filter on the category. So that percentage is quite simple to compute. And if I go on PCT, where I have already the code written, here it is. I divide sales amount by computing calculate sales amount all product subcategory. I remove the filter from the column that contains the subcategory. And that works just fine. If I try to write the same code, let me copy and we place it in the Snowflake. I already have the solution here, but we can get rid of that and we just write it. We write a new measure. Here, I cannot do product sub all on product subcategory, but as it happened before, we have a single place where I can remove the filter. I get rid of the filter from the subcategory table. Now, subcategory is one of the tables in my model. I already have PCT, so let me call PCT1, that I need to format as a percentage. And you see, the advantage is that now I have the table subcategory here, so I can remove the filter from here, and looks actually better than the original model. The problem is, if I place PCT1 here, it's not going to work. Look at the percentage shown here. It is never 100%. It always shows a smaller value. The only way to see 100% is to get rid of any filter, and finally you will see 100% here with the proper values there. That is, behavior is very different than what you have with the star schema, where you see the percentage is always 100%. And it does not matter whether I do have filters on the category or I don't. Why that? Well, this time the problem is with I lost my model. Where's my Snowflake? Here it is. This time the problem are expanded tables. If you need to write the code using the Snowflake, you need to worry about expanded tables. So you need to know that as soon as you remove the filter from the subcategory table, because of table expansion, this is going to remove the filter not only from subcategory, but also from category, because the subcategory expands actually to category. Because of the many-to-one relationship, removing the filter from subcategory actually kills the filter from category too. Not a big deal. If you spend some time studying and understanding all those details, you know that there are a lot of possible solutions. One is to use all except subcategory, and then we use a category. That is the standard pattern that we use whenever we need to work with expanded tables. So that now if I filter computers, you see that the value is computed the right way. The thing is, do you really want to spend time learning all the details about expanded tables, or do you really want to worry about that and think that your code might be wrong because you forgot about some details about expanded tables? So code that works perfectly fine on a star schema stops working as soon as you have a Snowflake schema. The model with a Snowflake is not larger, performance are not worse. It's not you only have more tables, so the model is harder to browse and harder to use from the user point of view, and you might have issues because of the DAX code. So you need to learn about expanded tables. That's why you can, for sure, decide to use a single flat table or a Snowflake. But actually, there are no particular advantages. And between the two, the single flat table is actually tempting, because if you just run simple queries, it looks faster. But if you look at the performance of an entire report or of complex dashboards, their performance is no longer an advantage. The model is way larger. 110 million rows resulted in 10 gigabytes. If you have a billion rows, that size is really massive and important. And the DAX code tends to be more complex because you do not have a place where you can remove filters or apply filters. The star schema is just perfect, even though it requires you to build the model the proper way. And a Snowflake, well, a Snowflake is not so much worse, but it doesn't even have advantages. So there are no particular advantages in using a Snowflake. You only have some small disadvantages. So again, what's the point about building a Snowflake instead of star schema? That was the last slide, and we still have 5 minutes for question and answers, if there are any. Before we leave the topic, remember about evaluating the sessions. You can take a picture or just look at the URL here. Providing feedback is extremely important and useful for as speakers for a lot of good reasons, because we fight for the best speaker, so that's the reason why we want feedback. And we actually learn by your feedback about what we did right and what we could do better. And there's also a prize, even though I don't remember what the prize is, for at the end of the day for people who leave feedbacks. So that's enough for the feedback part. If there are any questions, we have a couple of minutes. Otherwise, thank you. Oh my gosh, okay. No, otherwise, let's start with the question. Start. One thing, you need to talk very loud because I don't hear you. That's a problem.
In the denominator, in your single flat table, could
yes.
you have removed all filters from the sales one single table?
That's interesting. What if in the denominator of the single model, we removed everything from the sales table? We can look at that. In the fact table, here I'm removing filter from sales brand and sales color. Why not removing filter from sales entirely? Yes, that works. But by doing that, you are killing filter from any table, any column. So if as soon as I add, for example, on the columns a value, let's get rid of the sales amount, and for example, like we add the year, if only I find it, okay, the year on the columns, you see that I'm getting rid of the filter from the year, or the filter from the category, of any filter everywhere. That might be what you want or not. But in any case, you need to worry about all those details. You don't have a single place where you can say, I want to get rid of only the product part. Make sense? Thank you. There's a girl there at the bottom. No way. I did it. I repeated the question.
So over time, we've ended up adding more and more attributes to dimensions, so they end up the same granularity as our fact tables. Is that always a bad? It feels like a bad thing.
Say it again.
Over time, we've ended up adding more and more attributes to dimensions.
Yes.
So they end up on the same granularity as the fact table.
Okay. Is that bad? So the question was, if we keep on adding more and more attributes to the dimension, and we end up having the same granularity of the fact table, so where's the point in building the dimension if the granularity of the two are the same? Let me tell you, if you end up having a dimension that has nearly the same granularity of the fact table, that basically means the model was not designed the proper way. Because building a data model from the Kimball point of view really means identifying what is a dimension, what is a fact, and splitting the dimension into attributes that make sense from the user point of view. So you end up having groups of attributes that identify a product that have nothing to share with group of attributes that identify date or that identify store. So it's kind of unusual to have a dimension that has so many attributes that it has the same granularity as the fact table. Because at that point, it means that that dimension by itself could be split into different entities that make more sense from the user. Then, as it always happens with data modeling, there's not clear answer. I cannot tell you a rule that is valid forever. It's a matter of understanding the business needs and shaping the model in a specific way. Yep.
What's your general guidance for direct query models, both in the scenarios where you have access?
What's your general guide on direct query models? Well, the thing about direct query is that you should have a good reason to use direct query. So direct query is a tool. If you have a good reason to use direct query, go ahead and pay the price of super optimizing your SQL engine so that the queries executed by direct query are actually fast enough, knowing that you will never reach the speed of a Vertipack model. So you have to spend a lot of time optimizing your SQL model in order to obtain a speed that is just okay, not bad, not perfect. It's just fine, it works. The reason why you pay that price should be very clear to you. Most of the users I talk with that they implement direct query, they do it just because. And that is not a good reason, because you end up trying to optimize a model, find it extremely hard, and a model that could have been loaded in import mode be extremely fast without spending a single second of your life trying to optimize it because you are using the Vertipack engine, which is way faster. So what I tell to any user using direct query is ask yourself why. Why are you using direct query? Because the default should be import mode. You start creating your model in import mode, and you go away from import mode if you have a good reason. If you don't have a good reason and you're using direct query, you're just wasting a lot of time trying to make it fast enough to be acceptable from a user point of view. And you will never be able to obtain the same speed as an import mode. Yeah, if you are forced to use direct query, then you are in trouble, and you need to find a way to model to create the model the proper way. She's saying I'm out of time, which is also correct, but only 1 minute out. That for an Italian is absolutely outstanding. So thank you for watching the session. I will be here around for the next few days. So if you have any further question, don't be shy, stop me, and talking about DAX models and stuff like this is always a pleasure. Thank you.